Yes.
Okay, touch the leg, everybody. So, in today's video lesson, in fact, I'm going to continue with what we learned in the last video lesson. So, you remember learning about the wave nature of electromagnetic radiation, and there we talked about these properties of electromagnetic radiation. You've seen that these radiations, they can be identified with their properties, like you have wavelength, frequency, and then you saw wave number, and then combining these, you've seen that all these radiations, called electromagnetic radiations, they travel with the same speed in vacuum, that is the speed of light, which is 3.0 into 10 raised power 8 meters per second. That's it. And now, see, we've seen that there are different types of electromagnetic radiations which differ from one another in their wavelengths or their frequencies. So these different electromagnetic radiations, they constitute what is known as the electromagnetic spectrum. So this is the electromagnetic spectrum, and here in this picture you see the wavelengths. You see the wavelengths written here in terms of meter wavelengths. You see wavelengths increasing, right? And here at the bottom you are given the frequencies. The frequencies again, you will see the frequencies decreasing in this order. And here it's written increasing energy. So you will see this as we work on some problems. Like with increase in the frequencies of these radiations, you will see an increase in the energy. So like you see the frequency increasing from the right side to the left side, I should say. Like when the wavelength is high, the frequency is low, and when the wavelength is low, the frequency is high. So you can say, larger the wavelength, lower the frequency, then lower the wavelength, larger the frequency. That's it. So like you can see, you have these different electromagnetic radiations, like gamma rays here, with a wavelength of something like 10 raised power negative 11 meters. Then you have the X-rays, you have the ultraviolet rays coming somewhere here. Then here, in between 10 raised power negative 7 here, 10 raised power negative 6. In between these two, you have this visible light, the visible region of your electromagnetic spectrum. And the wavelength range, it's actually from something like 400 nanometers to 750 nanometers in terms of nanometers. So your visible light, it actually is a very small fraction of the electromagnetic spectrum. It ranges from 400 nanometers to 750 nanometers, which lies somewhere here, less than 10 to the power negative 6 meters in wavelength. And then next you have the infrared radiation, which is associated with the heating part, heat. And then you have the microwaves. Then you have the radio waves coming that side. So these are the different types of electromagnetic radiations that you have. Now, based on what we have understood so far regarding the electromagnetic radiations, and then their properties like wavelength and frequency, and then you also have something called the wave number, that is denoted by mu bar, and it's nothing but the reciprocal of the wavelength. Now, after this, we're going to work on some problems based on the wave nature of electromagnetic radiation. So let's take up some problems. Alright, now the very first problem I have for you is the wavelength of an electromagnetic radiation is 720 nanometers here. Find the frequency of the radiation. Find the frequency of the radiation. Okay, so this is the problem given to you. Now, the solution here will be, you know that the relationship between the wavelength, frequency, and the speed of light is nu into lambda, that is frequency multiplied by the wavelength of the radiation is equal to c, that is the speed of light. So you can use this expression here. What you're given here is the wavelength of the radiation. The wavelength is denoted by the symbol lambda, which is equal to 720 nanometers. And then this nanometer, you will change this into meter. 720 into nano is 10 raised to the power negative 9 meters. So you can leave it like this for the time being. And then the other thing that you have to now find is frequency, that is nu. You put a question mark here, and we know that the speed of light is 3.0 into 10 raised to the power 8 meters per second. So like we know that nu into lambda is equal to c, and now making substitution here, you have to find the frequency. So nu is equal to c by lambda, or c upon lambda. So you can write nu is equal to c is 3 into 10 raised to the power 8 meters per second divided by lambda is your wavelength. So that is 720 into 10 raised to the power negative 9 meters. So when you simplify this, let's see what we're going to get. It's a simple calculation here. This is 3 into 10 raised to the power 8 into, you take this in top 10 raised to the power positive 9. It becomes meter and meter, they get cancelled. The whole thing now divided by 720. If you want, you can make it 72 also. You can take one 10 on top. So that's it. So finally, when you simplify this expression, the answer that I have got is something like, I'll just write the answer straight away. It is, see, I'll put something like 0.00416 into 10 raised to the power, it is positive 17 per sec. We've got something like this. So if you do this division, you will get this answer. And now I want to write this in the scientific notation form. For this, what I do is I put this decimal point right after 4. That is, it will become 4.16 into 10 raised to the power. It's positive 17 here. Now I'll put it this way. Into 10 raised to the power. Since I've increased its value, it's negative 3 here per second, which is finally equal to, 3 digits. So 4.16 into 10 raised to the power 14 per sec. This becomes the frequency of the radiation, 4.16, okay, into 10 is power 14 per sec. Fine, that's it. Now, the second problem is for you to work out. I put it this way: the wavelength of an electromagnetic radiation is 450 nanometers. Now find or express this wavelength in terms of frequency. So you know how to write this. And the final answer here, if I'm not wrong, the frequency here is 6.7 into 10 raised to the power positive 14 %. This should be the answer. Now the third one for you is the wavelength of an electromagnetic radiation is 1500 angstrom. You will have to find the frequency of the radiation. Find the frequency of the radiation. Now, here the difference is you are given the wavelength in terms of angstrom. This is 1500 angstrom. Now, what you need to know is 1 angstrom is equal to 10 raised to the power minus 10 meters. You do this substitution, right? And then the answer here, the frequency is going to be it is 2.0 into 10 raised to the power 16 hertz or per second. This is the answer here. You work it yourself. Now, the next question is the fourth one here. It is the frequency of an electromagnetic radiation is 7.5 into 10 raised to the power 5 hertz. Calculate the wavelength of the radiation. Calculate the wavelength of the radiation. That's it. And now the solution here is you are given the frequency. So frequency is denoted by nu, and this is equal to 7.5 into 10 raised to the power 5 hertz. Hertz, it is the same as per sec. You can write this as 7.5 into 10 raised to the power 5 per sec. And then you are required to find the wavelength. Put a question mark here. And here once again the same relation you can use, that is C is equal to nu lambda, or you can write nu lambda is equal to C. So you write, we know that nu lambda is equal to C. Now what you need to find here is lambda, the wavelength, which is equal to C by nu. So now lambda is equal to C. C is 3 10 to the power 8 meters per second, divided by the frequency. The frequency here is 7.5 into 10 raised to the power 5 per sec. Now this per second will get cancelled, because when you take this on top, it will become second raised to the power 1. This is raised to the power minus 1, so these two will get cancelled. And the final answer here is going to be, it is 3 into 10 raised to the power 8 into 10 raised to the power minus 5 here, the whole divided by 7.5. So it is finally, this will be 10 raised to the power 8. So I'll give you the answer straight away. The answer I've got here, it is 0.4. 0.4 into 10 raised to the power 3, and the unit left here is meter, right? It's meter here. Now to express this in the scientific notation form, I need to have this decimal point coming after 4. So this becomes 4 into 10 raised to the power 2 meters. Right. So when I increase the value of the number here, I'll have to divide it. So by 1, that is 10 raised to the power 1, dividing by 10 raised to the minus 1, so it becomes. So this is the wavelength of this radiation. And now one problem for you to work out is Let's see. All right, now that's question number 5. Number 5. Here, the question for you is the frequency of. All right, the frequency of an electromagnetic radiation is 1500. This is kilohertz. Maybe I'll work it out for you. Calculate the wavelength of it. Calculate the wavelength of the radiation. Wavelength of the radiation. It's the same thing as this. Wavelength of the radiation emitted by the transmitter, same thing. Emitted by the transmitter. Now, the solution here. It's very simple. What you're given is the frequency in terms of kilohertz. So you must know that 1 kilohertz is nothing but 1000 hertz. So just to begin with, you can put your given frequency nu is equal to 1500 kilohertz. So you change, from the prefixes that are used in the SS system. Kilo means 10 raised to the power 3, isn't it? So this is 1500 into 10 raised to the power 3 hertz. Hertz, you can write this as per second. So this is same as 1500 into 10 raised to the power 3 per sec. Now you are asked to find the wavelength. So wavelength lambda is what you have to find. And then you can do the same thing. We know that like nu lambda is c. You put the value c here, that is 3 into 10 to the power 8 meters per second. And then your lambda is finally going to be c by nu, right? And then you will finally get the answer. The answer here happens to be, I got for you, this is 2.0 into 10 raised to the power 2 meters, right? It is the wavelength, so you can get it done yourself. And now the next problem number 6 is, I put it this way, the Tibetan section of VOA, this is a Voice of America radio. Washington broadcasts, broadcasts on a frequency of 1200, it is kilohertz. We calculate the wavelength of the electromagnetic radiation emitted by the transmitter. Radiation emitted by the transmitter. Same thing, emitted by the transmitter. So you can just do the same thing here. You just require to find the wavelength. Wavelength is what you need to find. You can just apply the same sort of relation here. That's nu lambda. That is nu lambda is equal to c. C is nothing but the speed of light, which is 3 into 10 raised to the power 8 meters per second. And the answer here, the answer I've got here, haven't done this myself. So we'll just work it out. Let's see. Okay. Solution for the sixth one. You see, you are given the frequency nu is equal to 1200 kilohertz, which is equal to 1200 into 10 raised to power 3 hertz, which is equal to 1200 10 to the power 3 per sec. The lambda, that is the wavelength. Lambda is what you need to find, and then we know that nu lambda is equal to c. So you need to find lambda, which is equal to c by nu. So lambda is equal to 3 into 10 raised to power 8 meters per second divided by the frequency is 1200 into 10 raised to power 3 per sec. And the simplification here, you can also get it done like this: 3 into 10 raised to power 8. This is meter per second, right? Per second cancels. So you left meter here. Take this on top if you want now. Okay, and here also what? Put it this way, 1 minute. I'll put this. This is, I can write this as 12 into 10 raised to power 2 into 10 raised to power 3 here. So finally, this is equal to 3 into 10 raised to power 8 into these two together, 10 raised to power 5. When you take it in top, it becomes 10 to the power negative 5, the whole divided by 12. So it is the same as your lambda is equal to 3 divided by 12. So it is 3 ones are 3 fours is 12. 1/4 is nothing but 0.25 into 10 raised to the power. It is positive 3. Therefore, your lambda here is, right, and this is the unit here is meter, right? This 1 meter is remaining. Alright, so the scientific notation form 2.5 into 10 raised to the power. I've increased the value from 0.25, it becomes 2.5, which means I'll have to now divide it by 10, right? So it becomes 10 to the power 2 meters. It is 2.5 into 10 to the power 2 meters. So this becomes the wavelength of the electromagnetic radiation emitted from this or by this transmitter from Washington, right? So that's it. And now another problem for you of the same type. Problem number, let's take this problem number 7. Okay, number 7 for you is this is another problem. The wavelength is the wavelength range of the visible spectrum extends from, this is interesting actually, from violet that is 400 nanometers to red with 750 nanometers. That's wavelengths. Now you're asked to express these wavelengths, in terms of frequencies, right? Or in frequencies. Very good. So now, when you write the solution for this one here, see, you're given the wavelength range of the visible spectrum. You saw the visible spectrum is from violet to red. So the violet color or the violet component of visible light, it has a wavelength of 400 nanometers, and then the red component or the red color light of the visible spectrum has a wavelength of 750 nanometers. Now you need to express these wavelengths in frequencies. So let's see. First thing is for violet color light, right? For violet color or violet component of the light. For violet color, you are given the wavelength, that is lambda to be, lambda is 400 nanometers. Now in nanometer you need to express this in terms of meters, right? So it is 400 into 10 raised power negative 9 meters. And now you need to find the frequency here. That is nu is equal to what? And next, we know the relation here between the speed of light, wavelength, and frequency. So you can just go ahead with that. We know that. What we know is nu lambda is c. What we want is the frequency here. It is c by lambda, right? So nu is equal to c. It is 3 into 10 raised power. Same thing. So 3 into 10 raised power 8 meters per second divided by the wavelength. Here is 400 into 10 raised power negative 9 meters, right? Meter and meter get cancelled, and you find left with per sec. That is the unit of frequency. And on simplification, the answer here, I'll just give the answers now. The answer here is finally it is equal to 7.5. 7.5 into 10 raised to the power 14 per sec, right? 14 per sec. This is for the violet component of your visible light. And then for a red component, for red color, right? Red color component, right? For the red color, see, you are given the wavelength to be 750 nanometers. And the answer I've got here for this is, frequency, right? It is 4. That is just 4, right? 4.0 into 10 raised to the power 14 per sec. So you must get this as your frequency for the red component of your visible light. So this is the sort of range in terms of frequencies from violet to red. It is nothing but 7.5 in terms of 14 per sec to 4 into 10 to the power 14 per sec. Okay, that's one thing. And then now the next thing is another addition here. So the next problem number 8 for you is, this time let's see, we will be asked to find the wave number as well. So question number 8, it says, okay, yellow light, it is yellow light, emitted from a sodium lamp, has a wavelength of 540 nanometers. Calculate the frequency. Calculate the frequency and the wave number of the yellow light. So now here you got to find two things. It's quite simple. First thing is finding the frequency. This we know. And the next thing is now wave number. This is what we have to find. So let's see. You are given the wavelength. Wavelength is given. So that's lambda. It is 540 nanometers, right? And nanometer here, nano we change it to meters, so it becomes 540 to 10 raised to the power negative 9 meters. You leave it like this for some time, and then you need to find the frequency. And you're also required to find the wave number. Alright, now you can easily find the wave number, and frequency you can apply the same rule, right? So let's put it this way. we know that, okay, new lambda is equal to C, and nu is equal to C upon lambda, and when you do the substitution here, the final answer which I have got here is this is the one, right? The frequency is 5.55 into 10 raised to the power 17. Yeah, it is 5.55 into 10 raised to the power 17 per sec. 17 per sec. Right? Now the next thing is with regard to finding the wave number, and we know the wave number is denoted by nu bar. It's given by the reciprocal of the wavelength. So this is equal to 1 upon the wavelength, that is lambda. You are given the wavelength to be 540. That is 540 nanometers, means 540 into 10 raised to the power -9 meters, which is equal to this 540. You can also write this as 1 upon 54 into 10 raised to the power -8 meters. So it's finally 1 divided by 54 into 10 raised to the power, so it becomes +8, right? It's 1 into 10 raised to the power +8 by 54. This meter, when you take it to the top, it becomes per meter, which is nothing but 1 by 54. The answer I've got here is 1 by 54, right? It is finally the final answer. If I give you straight away, I'll get this is 1.851 into 10 raised to the power 6 per meter. Per meter. This is in the scientific notation form. This is the answer you're supposed to get. And now moving on to the next problem. This is a homework. You will work it out yourself. So let's see, the next question is again of the same type. I'll just write it down for you. That becomes a question number 9, right? Question number 9 for you is red light emitted from a certain lamp. It is red light emitted from a certain lamp, has a wavelength of 720 nanometers. Calculate the frequency and wave number of the red light. Frequency and wave number of the red light. Same kind of question here, and you work it out yourself. And the answers I've got here, that is for the frequency, the answer is, if I'm not wrong, it is 4.17 into 10 raised to the power 14 per sec. And then the wave number, U bar, is 1.39 into 10 raised to the power 6 per meter. So these are the answers for you. Another last type, I should say, for you is question number 10 here. Calculate the wavelength, frequency, and wave number. Yeah. Okay, let's see. Calculate the. There are 3 things to be found out, I think. Calculate the wavelength, frequency, and wave number, of a light wave whose period is 2 into 10 raised to the power minus 2 seconds, minus 10 seconds. This is the time period. So the solution here, now you got to find many things. You're given the time, right? So what are the things that we are got to find? You're given the time given here is 2 into 10 raised to the power minus 10 seconds. That is the time period during which the waves passing a point is measured. So the time taken is 2 into 10 to the power minus 10 seconds. Very short period of time. So with the help of this, you can find the frequency. So this is something interesting. So frequency is actually the reciprocal of time. Frequency is the reciprocal of time, right? So your frequency here, nu here, is equal to 1 by the reciprocal of time. It is 1 by time. Here is 2 into 10 raised to the power minus 10, 6. This is equal to 1 by 2 is 0.5 into 10 raised to the power. When you take this into top, it becomes 10 raised to the power 10 per second, right? So this becomes a frequency, and if you write this in the scientific notation form, it becomes 5, right? 5 into 10 raised to the power. I'll increase the number from 0.5. It's become 5. So I have divided by 10, so it becomes 9 per second. This is the frequency. You got frequency now. Having got the frequency, it becomes easy now for us to find the rest of the quantities, that is wavelength. To find the wavelength now, see, we know that nu lambda is equal to C. So wavelength lambda is equal to C upon nu. That's the frequency. And you can now do the substitution here because we have already got the value for frequency, that is nu. And when you substitute the value of nu here, so the wavelength, the C is 3 into 10 raised to the power 8 meters per second divided by the frequency here is 5 into 10 raised to the power 9 per second. Per second, they get cancelled. So you finally have this is 3 into 10 raised to the power 8. You take this on top, becomes negative 9 minus 1 whole divided by 5, which is equal to 3 divided by 5. So it is 5, 6, that is 0.6 into 10 raised to the power negative 1. This is meters, right? Meters. When you write this in the scientific notation form, it becomes 6 into 10 raised to the power. You increase the number. Since you got the value increased, you have to divide it by 10. So minus 1, another minus 1, 10 is minus 2 meters. So now this is supposed to be the wavelength. So now you've got the frequency, you've got the wavelength, and the final thing is finding the wave number. Wave number nu bar is nothing but the reciprocal of wavelength. So your wavelength is 10 raised to the power minus 2 meters. I hope that's correct. So 6 and 10 to minus 2 is right. So you will do the substitution here, that is 1 upon 6 into 10 raised to the power minus 2 meters. This is equal to, when you take this on top, it becomes 10 raised to the power 2. 1 by 6, it is 1 into 10 raised to the power 2 by 6. This is per meter, you take this meter on top. So 1 by 6. So it is 0.1 something, no? So it is 0.16666, right? 66 into 10 raised to the power 2 meters per second. Or if you write this in the scientific notation form and put this 1.666 into 10, 10 raised to the power. Let me increase the value by, place the decimal point to the right by 1 digit. So decrease it by 1. It should be divided by 10. So it becomes as power 1 per meter. So it's 1.66. That's 2. So yeah. That's right. So 1.6 increasing the value by, so it is 10 raised to the power 1 only. So 1.66 into 10 raised to the power 1. That is waves or wavelengths per meter. So this is 1, right? Okay. And then finally, one problem for you to work out. That's the 11th problem, right? So the final one is of the same type. You just work it out, you try it out yourselves. So that problem is, let's see. Question number 11, problem number 11. So the thing is calculate the wavelength. You have to calculate, or you have to find the wavelength, frequency, and the wave number, of light wave whose period is 4 into 4. This is 4 into 10 raised to the power minus 12 seconds. This is the period. So now the answers I have got for you. Well, the frequency is found to be 2.5 into 10 raised to the power 11 per sec. Then the wavelength here is finally 1.2 into 10 raised to the power minus 3 meters. And finally the wave number I have got here is, the wave number is 8.33. It's 8. There it is. 8.33 into 10 raised to the power 2 per meter. So these are the expected answers. So if I'm not wrong, you're supposed to get these as your answers, right? For the wavelength, frequency, wavelength, frequency, and the wave number. You're given the period, that is time, during which the wavelength or wave passing through or a point is given, that is time is 4 into 10 to the power minus 12 seconds. Very short duration of time, very short. That's it. Now, after this, we are now moving on to the next part, and that is now the particle nature of electromagnetic radiation. There is the particle nature of electromagnetic radiation. So now here, talking about the particle nature of electromagnetic radiation. See, as I told you earlier, there are these two developments which played a very important role in the formation of the Bose model of atom. Bose model of atom. So the first one, in fact, as we are still discussing, it is the dual character or dual nature of electromagnetic radiation. There is electromagnetic radiations having wave nature as well as the particle nature. Now, as far as the wave nature of the electromagnetic radiations is concerned, we have already finished with that.